Welcome to the Deep Dive. This is where we take loads of source material, research, notes, articles, and basically boil it all down for you, giving you the key insights without you having to read everything yourself.
Yeah.
Today, we're diving into something, well, huge, global warming. But we're looking at it through the lens of a really unconventional, super theoretical idea for maybe tackling it.
And it is urgent. The research we looked at points towards potential warming of up to 7 Kelvin by 2100 if things don't change drastically. That means catastrophic sea level rise, truly extreme weather becoming normal. It's a really stark picture.
Definitely.
And the usual methods, like cutting emissions, they're vital, of course, but they're also slow. Maybe too slow on their own, given the momentum already built up.
Yeah, exactly. So for this deep dive, forget solar panels for a second. We're looking at this research preprint. It's called Exploring Orbital Dynamics to Mitigate Global Warming, a theoretical Earth-Sun system study.
Mm-hmm.
Our mission, really, is to get our heads around the physics here.
Wow.
Could you theoretically alter Earth's orbit as, like, an extreme form of geoengineering? And let's be super clear, this is not a practical plan.
Not at all.
It's a fascinating what-if based on physics.
Right. And it's grounded in real physics. They're using Newton's laws for gravity and motion, Stefan-Boltzmann for the energy and temperature side of things, and then using computer simulations to see what happens. It's not science fiction physics. It's established principles pushed to a theoretical extreme.
Okay, let's unpack that. How do they even start theorizing about changing Earth's orbit? What's the basic science link between distance from the sun and temperature in their setup?
Well, at its core, Earth's temperature, its equilibrium temperature anyway, is all about balance. Energy coming in from the sun, energy radiating back out, and that balance is heavily, heavily dependent on how far we are from the sun. That's where the Stefan-Boltzmann law comes in. It connects temperature and energy radiation. And Newton's law of gravitation, well, that just dictates how we move around the sun, the orbital path itself.
Okay.
So the researchers built this model using MATLAB. It basically steps through time, day by day, using numerical methods to calculate everything where Earth is, how fast it's moving, the energy exchange, and crucially, the resulting temperature based on those orbital parameters.
Right, so they had this digital Earth-Sun system. They needed a way to simulate changing the orbit. What did they actually change in the code? What was the variable?
They introduced something called the semi-major axis ratio, SR.
SR.
Yeah. Think of the semi-major axis as like half the longest diameter of an ellipse. It defines the orbit's size. SR is just a ratio comparing a potential new semi-major axis to Earth's current one. So SR equals 1.0 is our current orbit. Changing that SR value in the simulation let them model orbits of different sizes. And changing the size also affects the shape, the perihelion, the closest point, and the aphelion, the farthest point. These distances are key because they determine the temperature fluctuations during the year.
Makes sense. But before we jump into the results, how did they make sure this simulation wasn't just, spitting out random numbers? How did they validate it?
Good question. They did a couple of important checks. First, they ran it with SR 1.0, so simulating our current orbit. And the results were, well, pretty much bang on. The simulated closest point, perihelion, was 1.48 times 10 to the 11 meters. The known value is 1.47. The simulated farthest point, aphelion, was 1.51 times 10 to the 11 meters, exactly matching what we know.
It's pretty close.
Yeah, and the simulated year length, 365.25 days. Perfect. Then they looked at temperature. Their model baseline for Earth, SR 1.0, gave an average temperature of 254 Kelvin.
Okay, wait, 254 K, that's like minus 19 Celsius. Earth's average is much warmer, around 288 K, right?
Exactly. And that difference is because their model is simplified, it doesn't include the greenhouse effect. It's purely looking at the temperature based on solar radiation and distance. But that's actually okay for their purpose because they're interested in the change in temperature caused by orbital shifts, the relative difference.
I see. So it shows the impact of the orbital change itself.
Precisely. And to double check that, they simulated Mars-like conditions, setting SR near Mars's value, around 1.3. The temperature it calculated matched Mars's known average, so the relative physics seemed solid.
All right, validation checks out. Now for the fun part.
Yeah.
What kind of wild results did they get when they really started cranking that SR dial way up or down?
Oh, it got pretty extreme. So, take SR involves 0.7. That means pulling the orbit in significantly closer on average. The simulation showed the perihelion shrinking way down and the aphelion staying similar to Earth's current perihelion. The result, massive temperature swings, like a peak temperature hitting 446 Kelvin. That's 173 Celsius, hotter than boiling water. The minimum was 254 K, their baseline, but the average shot up to 307 Kelvin. Pretty warm.
307 K average. And the year.
Super short. just under 197 days.
Wow. Okay, what about going the other way, pushing the orbit out, SR greater than 1?
Right, so they tested SR 1.3, a much larger orbit. Here, the perihelion stayed somewhat similar to Earth's current orbit, but the aphelion, it went way, way out, 8.16 times 10 to the 11 meters, and the planet became incredibly cold. The max temp was only 254 K, the model's baseline, but it plummeted to a minimum of 109 Kelvin. That's like minus 164 Celsius.
Freezing, absolutely freezing.
Totally. The average was just 137 Kelvin in the year.
Yeah.
It became incredibly long, 2,117 days.
Over 2,000 days. So yeah, messing with the orbit, even theoretically, has these just enormous consequences for temperature and the length of the year. Mind-boggling. What about more subtle changes? Did they look at SR values closer to 1.0?
They did. They looked at values like 0.95, 0.975, then 1.0, 1.025, 1.05, kind of zooming in around our current situation. And the pattern was, pretty clear and logical. As you nudge SR slightly upwards, increasing the average distance, both the perihelion and aphelion distances tend to increase a bit. The average temperature in their model goes down, and the year gets longer.
Okay, give us an example.
Sure. So SR 1.0, that's the baseline, 254K average temp, 365.3 day year. Increase SR just a bit to 1.025. The average temp dropped to 247K, and the year stretched out to about 395 days. Almost 394.9 days.
A 7 Kelvin drop for that small change in SR.
Yep. And if they went a little further, SR 1.05, the temp dropped again to 241K, and the year became about 430 days long.
Okay, so this is where it connects back to tackling global warming, right? How do they use these numbers to propose a specific theoretical orbital tweak?
Exactly. They looked at the projections, roughly 2 Kelvin warming already happened, plus a potential worst case 5K more by 2100. So that's a total of 7 Kelvin warming they needed to counteract. In their model's terms, starting from the 254K baseline, counteracting 7K of warming means aiming for a target average temperature of about 247 Kelvin.
And the simulation showed
that setting the semi-major axis ratio, the SR, to 1.025 resulted in pretty much exactly that, an average temperature of 247 Kelvin.
Right. So SR 1.025 is the magic number in their model for a 7K cooling effect. What does that actually mean for the orbit, like in terms of distance in AU or kilometers?
It translates to shifting Earth's average orbital distance from 1.0 AU, or current average, out to approximately 1.0578 AU. So a bit less than a 6% increase in the average distance.
How does that change the shape, the closest and furthest points?
It means increasing the perihelion distance, the closest point, by about 0.01 times 10 to the 11 meters, roughly 10 million kilometers further from the sun at closest approach. And the aphelion, the furthest point, increases more significantly by about 0.15 times 10 to the 11 meters, so 150 million kilometers further away at the farthest point. The orbit becomes slightly larger and a bit more stretched out, more elliptical.
Okay, slightly bigger, slightly more elliptical orbit,
Right.
leading to a 7K cooling. And the inevitable consequence for the year.
The orbital period, the length of the year, changes to that 394.9 day figure we saw, basically 395 days.
So there it is, the theoretical fix, according to this study. Nudged Earth out to an average of 1.0578 AU. That cools the planet by 7K, potentially offsetting warming, but adds about 30 days to our year.
That's the core theoretical finding, yes. An orbital radius increased to about 1.0578 AU could theoretically lower the average temperature by 7K based on their model. But the year becomes 394.9 days long.
And we have to keep stressing, as the paper itself does, this is purely theoretical. They explicitly state it's impractical with current technology and has massive logistical challenges, not to mention ethical ones.
Absolutely. It's a thought experiment. But its value isn't zero just because we can't do it tomorrow. It really underscores how sensitive planetary temperatures are to orbital dynamics. It pushes the envelope on geoengineering ideas, contributing to the whole discussion about climate solutions, even the really out there ones. It encourages scientists to think big,
Yeah, and for you listening, it puts the climate challenge into such stark perspective, doesn't it? I mean, if scientists are running calculations on moving the planet, even just theoretically, it shows the sheer scale of what we're up against.
It really does. So, the key takeaway. A theoretical orbital shift might cool Earth, but it's impossible now and would change our year forever.
Which leaves us with a pretty heavy thought to end on. If solving climate change, even just on paper, might involve fundamentally altering something as basic as the length of our year, what does that truly tell us about the magnitude of the problem? And maybe more importantly, what does it suggest about the potential unforeseen consequences of any large-scale geoengineering, even the stuff that seems less extreme than moving planets? Where's the line between fixing the climate and fundamentally changing the Earth we're trying to save? Someone to definitely keep thinking about. That's it for this deep dive.